Welcome back to lesson 7 of composition and inverse functions, and this lesson is called inverse functions and their graphs. Okay, so grab your note-taking guide and let's look through this together. Okay, first part 1, we're going to have to do the definition of what one-to-one means. So let's zoom in just a little bit so you can see it. Okay, one-to-one, a function for which every element of the blank of a function corresponds to exactly one element of the blank. Okay, a one-to-one correspondence is when a function's domain has a unique and exactly one element matches with the range. So you don't have any repeating values in the domain or in the range. They're all unique to each other. So you can't have more than one value repeating in x's or more than one value repeating in y's. They all are unique values. Okay, line tests. Line tests help us see them more from a graphical approach. So you may have learned the vertical line test. Okay, line tests help us to see one-to-one relationships. The function f of x has to pass a vertical line test to be considered a function, and you probably did this in middle school. Okay, but to show one-to-one, it has to pass both a vertical line test and a horizontal line test. So not only does it need to only touch the graph in one spot vertically, but also if I turn my pen, I can do it horizontally. Okay, now this one doesn't pass the horizontal line test because it touches a graph in more than one place, doesn't it? As you can see, it's touching in 3 places right here, 1, 2, and 3. Okay, so this one does not have a one-to-one correspondence. Now let's talk for just 1 second about why that would be true. The reason why that would be true is, remember, inverses switch the x and y coordinates. So when you switch the x and y coordinates, you have to have the vertical line test will basically become a horizontal line test because a vertical line and a horizontal line are inverses of each other. So it's that other test that you're looking at. Okay, so let's look at the second one. Now this is just a linear function. Okay, does it pass a vertical line test? Yes, it passes. Let's go ahead and fill that out. Yes, that one passes the vertical line test. Does this one pass a horizontal line test? Oh, this one passes. It only touches in one place. So this one is a one-to-one. Okay, so let's go back to this one and just fill this one out. This one passed the vertical line test, didn't it? Remember, it only touches in one place, but the horizontal line test, we said that one was a no. So this one is a no on the one-to-one correspondence. Okay, so now let's go down and look at the cubic function. Okay, we have a cubic function here. Let's try the vertical line test. Okay, remember this is always increasing, kind of flattens out, but a cubic function is always increasing. So that one does pass the vertical line test. Okay, now let's switch and try the horizontal. Yep, that one's also passing a horizontal line test, so that one does have a one-to-one correspondence. Okay, let's try the absolute value graph. Okay, let's see, vertical, it's passing, it only touches in one place, so that one's a yes. How about a horizontal? Well, there's no graph down here, but look, once we hit up here, we're crossing in 2 places, aren't we? We're crossing in quadrant 1 and quadrant 2. So this is a no. So this does not have a one-to-one correspondence. Okay, so hopefully that little visual will help you with those. Okay, the second part of what we need to look at today is just some notation. Okay, so we're given g of x is equal to 2x and h of x is equal to x squared plus 3. And we're going to find h of g of 5. You haven't seen that notation. Well, that notation is actually exactly the same as a composition. So it means the same thing as h of g of 5. So let's just evaluate that. Do you remember how to do that from a couple days ago? Or a couple lessons ago? We're going to plug 5 into the g function first, then take that output and plug it into the h function. So let's work through that. let's plug in 5 into the g function. So we have g of 5 is equal to 2 times 5, which is 10. Okay, from there, we're going to take 10 and plug it into the h function. So h of 10 is equal to 10 squared plus 3. So that's 100 plus 3, which is 103. So that function is equal to, or that composition is actually equal to 105. Okay, so now let's try something totally new. Let's try a triple, okay? G of h of g of 2. Okay, what do you think we do with a triple? Well, we're going to work backwards. We're going to take 2 and plug it into the g function. And then we're going to take that answer and plug it into the h function. Then we're going to take that answer and plug it back into the g function for a second time. So let's try this one. Okay, so our g function is 2x. Okay, so let's start with that one. Let's zoom out just a little bit so you can see. There you go. And we're going to plug a 2 into that. So 2 into the g function gives us 2 times 2 or 4. Now we're going to take that 4 and we're going to plug it into the h function. So we're going to take h of 4 and we'll have 4 squared plus 3. Well, 4 squared is 16, 17, 18, 19 as our output. Then we're going to go back and plug 19 into the g function. And that's 19 times 2, or 2 times 19, which is what? 38. So that composition, that triple composition, the actual value is g of h of g of 2 would be 38. Okay, I've given you one to try, and the answer will be in the course. So you can go back and pause right now and work that, or you can wait till the end of the video and check it. Okay, I'm going to keep going and we're going to look at some graphs. Whew, we got a lot to do today. Okay, now let's look at some graphs. Okay, first of all, we're going to try to work on graphing inverses. Well, remember, graphing inverses, we're actually just switching ordered pairs. So when you're given a set of ordered pairs like in this problem, all we're going to have to do to graph it is just switch our x and y coordinates. So let's look at this table here. Our x is 0, 1, 2, 3, and our outputs are negative 1, 1, 3, and 5. So all we're going to do is switch positions. So I'm going to make this negative 1 and this 0. Well, 1 and 1 are switching, but they're still the same value. I'm going to switch the 3 and the 2, so 3 and 2, and then I'm going to switch these, and that's going to be 5 and 3. Okay, so all I've done is switch my ordered pairs. Now let's plot our two different functions. Let's start with this first one. Okay, I'm going to plot these points 0, and remember these are one under the other, so you may want to write it as an ordered pair. 0, negative 1, that's my first point. My second point is 1, 1. My third point is 2, 3, over 2 up 3. And the third one is 3 and 5. 3, 1, 2, 3, 4, 5. Okay, so it looks like a linear function, doesn't it? It's just a linear function. And now it's inverse. Okay, the inverse is negative 1, 0. So I'm going to write this one as an ordered pair. Negative 1, 0. So this point has just mapped over to here. 1, 1, it's actually in the same spot, isn't it? Okay, and then this next one is now 3, 2 instead of 2, 3. So 1, 2, 3, 1, 2. So notice this one has mapped over to here, and then this one is 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. Okay, so here is the inverse function. Okay, so let's label these. This first one is f of x, and the second one is f of negative x. Okay, my inverse function. And what has happened is I'm actually finding the inverse because there is a line of reflection. Okay, I don't know if you can see it yet, but you'll be able to see it after today. your line of reflection is actually this line right here. So if you folded this paper and made these two lines line up, you would fold it along that line. Well, what line is that? That's the line of reflection for inverses, which is y is equal to x. Y is equal to x is the line of reflection to find the inverse graph. So just take your original function, fold it over that line, and you get the inverse function. It's really pretty easy. Okay, so now let's look at the three graphs on the next page. We're going to try to plot these points. Okay, let me get this in the screen so you can see it. There you go. Okay, let's start with a parabola. Okay, I've given you a couple graphs that already have some ordered pairs on them to make it a little bit easier to start with. Okay, so 0, 0. If I'm going to graph the inverse of that, guess what? The inverse is still just 0, 0. It's not going to move. So I'm just going to darken that spot. Okay, this point though, -1, +1, is going to reverse to 1, -1. So that means I'm going to go over 1, down 1. So it's going to move to right there. This one is 1, 1, and it's not going to move. We just saw that point a minute ago. It doesn't move because x and y are the same. This one is 4, or -2, 4, so it's going to become +2, +4, -2. And this one is 2, 4, which becomes 4, 2. Okay, so as you can see, this parabola was facing up. Now, what's happening to this parabola? It's actually facing to the right, isn't it? Well, I didn't get that perfect, but you can see. Okay, now notice, if I drew that line of reflection in here, that y is equal to x line, you can see that if I fold it, it folds upon itself. So it's taking that parabola, it's facing up, and it's now facing to the right. Kind of cool, huh? So I like to start with ordered pairs and map a couple of them to get a sense of where my graph is going. Okay, so there's the parabola. Now let's go to the line. Okay, on this line, we have a couple of points drawn. We have the point 2, 0. Well, think for a second. 2, 0. Where is it going to map to? It's going to map to 0, 2. Okay, now this one, so now that is 0, 2. Let's go ahead and label a couple of them. This one's going to be 1, 2, 3, 4. So this one's 0, -4. So it's going to go to -4, 0. So it's going to map to here. So let's see, if I draw a line, I'm just going to kind of sketch it here. A line through there, look what's going to happen. That is my inverse. So this black line is my inverse. Now notice, right, if I were to draw the y equals x line, the line of reflection, see where it would be? It would be right there down the middle. So this dotted line is your line of reflection. The black line, and I'll darken it just a little bit more, is actually the inverse. Okay, we'll call it f of -x. And there's your inverse to that original line. Okay, third one, just to get a good grasp on what's going on, I think we have a cubic. Let's look at the cube for a second. There we go. Okay, here's our cubic one, and these get tricky, okay, because we have so many bumps. But the best thing I can tell you is just pick a couple points and graph them, and then you can get a sense of where it's going to go. Okay, this one's 1, -1, so that means it's going to be -1, 1. So the point here is going to map over here. Okay, this point right here is 0, +1, so it's going to be +1, 0. Okay, this point right here is -1, 3, so that one's going to be 3, -1. Okay, so I've gotten a low, crossing an intercept, a high. Let's try to get this other intercept. I'm going to estimate this a little bit. This looks like it's -2, 0. It's kind of close to that, so we're going to estimate that to -2, 0, which would be 0, -2, or not quite to -2. And then let's pick one on this other side here. Let's pick maybe this point right here because it's pretty good. So that's 2, 3. So that means it's going to be 3, 2. Okay, so now let's try to put all these together. Okay, I may get it right, I may not. Let's see. Looks like it's coming down, bumping up, and then back down again. There we go. Okay, it's not perfect, and yours won't be either, but I'll curve it out just a tiny bit more to get, there we go. That looks a little better. Okay, so there's the inverse. Now, the line of reflection is right here on the y equals x line. And you can see, yes, that got reflected over, didn't it? Okay, it's got so many parts that it's kind of hard to see, but you can see that the line did get the graph did get reflected over the y equals x line. So there you go. That's the whole lesson. I hope this video was helpful and you can do well on your assignment.